Okay, so welcome everybody to this installment of the Institute of Astrophysics seminar. Today is a very special seminar because we're welcoming Costantino to the Institute and then we're saying goodbye to Costantino. We will be very sorry to miss him, but it's for a great cause because he found a permanent position in Sapienza. So that is great. We're cheering for him, and please come visit often.
Yes, great pleasure.
After you start. So Costantino did his studies, both masters and doctoral work in Italy, Bologna, and
Sisa.
Yes. And then he moved for postdoctoral positions and it was Rome and Milano. And then he joined the Institute of Astrophysics. This is his welcoming seminar so that we can welcome him and learn more about what he's doing. He's in Maria Harris's group and in transit towards his permanent position, for which we will cheer him on. So welcome, goodbye, and the floor is yours.
Yeah. Thanks. Okay, yeah.
Yes. Oh, yes, so that people can see. Next to the microphone, if you click start video. There.
So, but where do they see me?
I see you. So good. See?
Okay. Okay. Great. So, yes, I was supposed to present my research lines for joining the group, but yeah. So, what I want to do in this talk is to showcase some applications of machine learning and deep learning to the data analysis of gravitational waves. It would be a very partial, of course, overview, because it would be based on works that I've done recently, but there are many such works in the community that have been done. So these are the works that I will be based on, and with such great collaborators, Riccardo Buscicchio, Shweta Bhagwat, Roberto Podesta, and Davide Cirosa and Francesco Nobili. So, okay, come on. Yeah, okay. So a little bit of motivation. So what you see on the left is the so-called stellar graveyard plot, which shows the black holes and neutron stars that have been observed so far. In particular, the blue dots are binary black hole mergers observed by the LVK collaboration. And you see they are many, so order of 200s right now, with the O4A release that was recently released. And but we expect much more in the future, like in the medium run. Because, so if you see this plot, this shows sensitivity curves for gravitational wave ground-based detectors. And we are here, and we expect to be here in the beginning of 40s, let's say, 2040s. So there will be an order of magnitude increase in the sensitivity of gravitational wave detectors if they are built, because, this is not yet officially approved. It's not, so there is efforts both in the US and in Europe to make them funded. Okay, like in particular Einstein telescope in Europe, Cosmic Explorer in the US, we will see, but hopefully at least one of them will be built. And so, but even if they are not, there is LISA that has been already approved, and it would be a similar sensitivity increase. And this is official. LISA will run in space. So, but why do we expect such wonders from future detectors? This is because, so if you look at the stellar formation rate, so you see that they peak around the redshift of 1 to 3, and so also the binary black holes population should peak around the same redshifts. But if you look at current gravitational wave detectors, like here, they do not have a very large horizon, in terms of redshift. They cannot observe much past redshift 1. So we expect, actually, if future detectors like Einstein telescope and Cosmic Explorer are built, they will be here. Okay, so they will have an horizon which will go up to redshift 10. Okay, so we will be sensitive to most of the BPH population. So, which means that we will have many more detections, but also much louder detections. So this will allow to transition towards a precision era of gravitational wave astronomy. And this will be precise for both reasons. Precise in the sense that you have individual, very loud observations, but also you can reach very precise conclusions by combining many dimmer observations. So what do you want to learn with this precision? So many things. These are not all, of course. So you can do astrophysics, like for example, how do BPH assemble? You can do cosmology. So how does the universe on the large scale evolve? But also fundamental physics, which is what I am mostly interested about. And you can do the fundamental physics of both black holes and neutron stars. So why you can do fundamental physics of black holes? For the reason that black holes are purely gravitational objects in general relativity. So when you want to understand if general relativity is the correct description of black holes, or if you wish, of the space-time around black holes, so there is no better way, because you are observing gravitational waves from a purely gravitational object. So let's say the signal is not contaminated by other effects. With neutron stars, it's the opposite. So why there is efforts to test gravity also with neutron stars, but this is more difficult because you have matter effects, of course, because it's a neutron star. And but what you can do is actually to probe the composition, the inner layers of neutron stars, like how is the neutron star composed? There is big theoretical uncertainty right now on this topic, and neutron stars are one of the windows through which you can explore this fundamental question about not gravity in this case, but about fundamental physics, in particular fundamental nuclear physics. But in this talk, I will focus more on the first question. So what we can understand of the description of gravity, is GR correct? This is basically the main question in this respect. And okay, I will skip this plot. But this plot is just saying that with gravitational wave detectors, what you are sensitive to is the strong region of gravity around very compact objects, which is a novel region of inquiry. I mean, other experiments do not explore the same regime. So that's why it's interesting to look at testing general relativity with gravitational waves, because they are sensitive to a parameter space where other experiments were not sensitive before. However, there is a main difficulty that you do not have a competing theory that has the same, let's say, glory, the same level of development of general relativity. So general relativity is very well understood, both theoretically and numerically. And for beyond GR theories, this is not the case. Okay. So, of course, there is a lot of theoretical understanding. There is very recent, let's say in the past 10-ish years, there have been a lot of developments in the numerical relativity understanding of theories of gravity that are not as simple as general relativity, but it's not yet at the level of saying, okay, we can compare apples and apples, okay? So, since we have so much more understanding of GR, it would be unfair to compare GR with another theory, and like in the classical, theory 1 versus theory 2 framework. So what you do is more diagonal. So you introduce the so-called deviational parameters. So in particular, you start from GR, then you have a parametric expression of the so-called waveform that is emitted by a binary black hole event, and then you introduce deviations in the waveform, like in the form of deviation in the parametric expression of the waveform, in such a way that you tune these deviational parameters such that when they have a particular value, most of the time it is 0, you reproduce GR. And then you promote these parameters as parameters that you measure, much like the other properties of the event. For example, what are the masses? What is the distance? What is the redshift? What is the value of the deviational parameter? Okay, so you have this increased parameter space with deviational parameters, and you can do this wherever in the waveform. But in particular, let me claim that it's very interesting to do this in the final portion of the waveform that is called the ring down. So what is the ring down? When the binary black holes merge, they produce a remnant that is a black hole as well. And this black hole initially is deformed and it emits gravitational waves. And these gravitational waves are carrying away a little bit of energy, but are also carrying away structure, okay? And then at the end, they leave what is known as the Kerr black hole, okay? So like the unique, so we all know, okay? So black holes in general relativity are very simple because they can be described by the Kerr metric, but black holes at equilibrium can be described by the Kerr metric. Black holes outside equilibrium, they are not described by Kerr metric, but they are described by by Kerr metric plus perturbations if they are close to equilibrium. And these perturbations, it was shown, like decades ago, that they are transported away by gravitational waves, and then at the end you remain with a remnant that is called, with a remnant that is a Kerr black hole, okay? So this is the standard picture of general relativity. And what is notable is that if you look at the spectrum of the gravitational waves that are emitted by the remnant, they are not emitted, at random frequencies, but they are emitted at very special frequencies that are called quasi-normal modes. And in particular, quasi-normal modes are complex frequencies. So there is the real part of the frequency where the spectrum, like the power spectrum, would peak. And then you see the wave is damping, as you approach equilibrium. And so you have damping times. So at the end, the signal is very simple. Like the mathematical description of the signal is a superimposition of sinusoids with special frequencies and special damping times. And this LMN, they are just, so LM is so when you expand the perturbation equations in spherical harmonics, and N is overtones. So like the same as you have with the guitar, no? That you have several tones of the same note. So the idea is very simple then. So if you look at these frequencies and damping times in general relativity, they can be predicted very, very well based on perturbation equations. And they only depend on the mass and the spin of the remnant black hole. So if you measure multiple modes, not only one, so you have many quantities that you measure, but they should lie on a two-dimensional hyperplane, let's say, okay? So then, of course, you do not formulate this in this, in this mathematical geometrical fashion, but just to understand each other, so that they should so you should have a collection of at least 3, hopefully many parameters, but they cannot be random. They should all be connected by a two-dimensional parametric relation, okay? And this is the test that is called black hole spectroscopy. So if a black hole passes this test, you would claim that you didn't find any contradiction with general relativity. Now, okay, so this is a work, this is not machine learning, okay? This is much simpler. So this is a work that we did to understand what is the prospect of black hole spectroscopy. Because if you look at it now, so LVK is operative, so like it's measuring things since 10 years, and there are only few events for which you can address the spectrum of the remnant black hole, and not with much precision. Like, for example, here you see, so this is a deviational parameter in the spectrum, and you measure it with a precision of 10% right now, which is the typical precision that you have nowadays. And it's not very precise because, we do not expect for sure 10% deviations outside general relativity in black hole ring dumps, or at least I do not. If we find 10% deviation, I would be super surprised because, I guess we should have found big deviations already also in other regions as well. So the aim is, to improve the precision of black hole spectroscopy. And so we tried to understand what can you do with future detectors, and in particular ground-based detectors here and space-based detectors. Basically, these are here. So what we find, okay, for space-based predictions are very uncertain because you don't even know what is the BPH, the massive BPH population. No? So there is big uncertainty on how many supermassive binary black holes are there in the universe. So it could be that you will observe only one event. It could be that you will observe thousands. So at least, I mean, that's the best that you can say. So predictions for space-based missions are very uncertain in this respect, while they are much more robust for ground-based because we know more about the population of stellar mass binary black holes. And so what we found is that, so what we expect to find if ET is operative or if ET and CE are both operative is to detect thousands or even tens of thousands of ring down per year, which is these numbers here, with a precision similar to ours, sorry, to the precision that we have right now, so 10%, let's say, okay? So you might say, okay, it's still not a very nice precision, correct? But now it's not 3 events, now, or 4 events. Now it's 10,000. So you understand that combining these events together will give you very tight constraints on deviations from general relativity that you cannot obtain now at the same level of precision, just because the observations are not enough. The number of observations are not enough. But then you also have, like here, for example, you also have a handful of events with SNR 100. So just to give you an idea, this event, this has SNR order of 10, okay? So which means that, so you will have a handful of events which are 10 times louder than that event in the previous slide, and also outliers. So this was from synthetic catalogs. So we might never observe such high SNRs. They could be outliers of the catalog. So, but we just wanted to point out that depending on the catalog, we found sometimes, depending on the realization of the catalog, we found sometimes even SNRs of order 1000, but very rare. So I find this, exciting enough to go on with this scientific program of testing GR with black hole ring downs. Now, if you want to combine, so it is immediately clear that combining multiple observations from the previous numbers, it is clear that it's pivotal to obtain robust tests of general relativity with future detectors. When you combine multiple observations, so you have a problem. If you just multiply the posteriors, like naively, so you have a measurement, so you have a probability density for your parameter, deviational parameter, and you multiply the posteriors for all the events together. So you can do that, you obtain a very tight constraint, but this is wrong because this, so there is an underlying assumption when you do this, which is that the deviational parameter is the same for all events. And this is wrong because, I mean, like the deviational parameter is not the fundamental parameter. It's an effective description of how GR is modified. So what you have typically is you start from a theory that is not GR, so you have GR plus other terms in the Lagrangian. So the fundamental parameters will be the coupling constants, let's say, of these other terms in the Lagrangian. And so then you have to derive the solutions, and then you have to perturb the solutions, and then you have to solve the perturbation equations, and then you have your new frequencies and damping times. So it will be a very non-linear path that starts from the mass, spin, and coupling constants, and ends at the value of the deviational parameter for this mass and this spin black hole, even the coupling constants. So this non-linear dependence means that you should not expect the same deviational parameter for all events. So instead of multiplying all the posteriors, great. Yes. Instead of multiplying all the posteriors together, so you follow another approach, which was pioneered in this paper, which means you do a so-called so you do hierarchical inference, which is the same as doing population analysis. What does it mean, population analysis? Okay, I will not go through the mathematical details, but it means that you are not modeling the deviations as a number, but you are assuming that these deviations come from an underlying population. Okay, and for simplicity, right now they assume, I mean, they know that it's not, but for simplicity, they assume that it is a standard normal population with a mean and a standard deviation. And so when mu is at 0 and sigma is at 0, you recover GR. Okay, this is important. You do not recover GR when mu is at 0, but when both are 0, because it means that the deviations are picked up from a delta distribution centered at 0. Okay, this is GR linked. So just seeing that, you know, that this number peaks at 0 is not enough. This is important. So right now, this is, so I should say probably I'm not part of LBK. So I don't know what's happening right now in the collaboration with testing GR. So they have not yet published GWTC4, but they have data from GWTC4A. So that they will be out soon. They were supposed to be out in August, but then I don't know what happened and they are not out. But they are analyzing the data. But right now, this is what is there on the GWTC3 paper, which dates back to 2021. So when they combined all the multiple observations together, so you see they obtain very loose constraints. So this is a constraint on the deviational parameter from the F2 fundamental oscillation frequency of the black hole. And you see, I mean, the constraint is very loose. It's 50%. So for sure, yeah, it's consistent with GR, but with this level of precision, we didn't expect to find a 50% deviation. Here it's similar, it's another approach, but so it's probing the fundamental 220 frequency and damping time. And so they see, so you have to look at the black curves. So they see that like frequency-wise, this is consistent with GR. Damping time-wise, it is consistent, but it's peaking a little bit away. I mean, not enough to say, okay, this is not in the tail, this is not 5 sigma, but this is a consistent shift. Like as more events were added, the more this shift was observed. So it's interesting. I mean, so if I have time, I have something to say about this in the last slide. Now, okay, now what about application of machine learning? So we recently, asked the following question. So how can we incorporate this fact that these deviational parameters, they also depend on the non-deviational parameters? So if you look at this hypothesis of what is the population of the deviational parameters, is not dependent on the other parameters. These mu and the sigma are assumed to be fundamental numbers. Okay, we know it's not true. I mean, we know that this delta phi, this deviational parameter, will depend on, for example, the spins of the black holes or the masses or both. So can we extend this hierarchical inference framework to allow for these dependencies? Yes, but then there is a problem. Like if you just impose a functional form, you are restricting yourself. Like you can say, okay, let's look for, I don't know, polynomial dependencies, or let's look for logarithmic exponential dependence. Yes, but this is very restrictive. And even if you say, okay, but this is a Taylor expansion, so it's always polynomial. If you do a Taylor expansion, it's true, but it's very inefficient. So it can overfit, it can converge slowly, and also if it is an expansion, it means that it's localized, so it will be localized around a precise corner of the parameter space, the one that you are expanding about, and this description will not be very precise outside. So as further you go from this special point that you are expanding about. So we decided to follow another approach, which is a non-parametric machine learning technique called Gaussian process regression. So basically, the idea is that you do not impose a functional difference, but it reconstructs sorry, functional dependence, but it reconstructs your functional dependence without telling what should be the shape. So how does it work? So this is a basic plot of how GPR, Gaussian process regression, works. So so this is a simple example in which you have one independent parameter and one dependent parameter. So you want to reconstruct y equal f of x. So you have some special points in your domain that are called nodes, and you are free to move the function at x1, x2, and x3 up and down. And then you ask, what are all the possible, red curves that pass through the values that pass through y1 at x1, y2 at x2, and y3 at x3. And you want to optimize y1, y2, and y3 given the data, blah, 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 in such a way that they maximize some definition of, likelihood. But then at the end, you will have all the functions that pass through, okay? And wait, there is another slide if this is not clear. So now what is the point? So this is a Gaussian process, which means that in principle, you are extracting all the points, not just this, and this, but also the intermediate ones from a Gaussian. So why it doesn't produce noise? So in principle, you might say, okay, if I'm extracting a Gaussian in this parameter space for each point of the x-axis, I should just get some noise, no? So the trick is that you are not assuming that all points are uncorrelated. So you are assuming that the draw at x1, the draw at x1, at x, I don't know, 1/2, x2, 2/2, x3, they are not independent draws, but there is a very big correlation matrix, okay, that correlates the outcomes at different locations. And this is similar to what is called the kernel trick in machine learning, but basically, so the trick is to say that this k minus 1, which is the covariance matrix, is not a constant, okay, but it is space dependent. Parameter space dependent, okay? So this is the trick. So we tried to do, so for example, one of the parameters here will be the so-called correlation length. So which is telling you how much correlation there is between my draw here and my draw here. So if the correlation is too much, the draw here will basically determine all the other draws. So there will be a constant if there is too much correlation between this point and this point. If the correlation is at 0, if the correlation length is at 0, so you recover the previous hypothesis of basically noise, because there is no correlation between what happens here and what happens here. So if there is no correlation, you are going back to the hypothesis that you just have noise. So you can play with this parameter and other similar parameters to reproduce, so basically to sample not points, but to sample functional dependencies, okay? And this has also the nice feature that if you sample in a place where you don't have observations, you have not gauged your functional dependence there. So whatever is your functional correlation length, if you go too far from the last data, you will be very uncertain because, I mean, there is no other point that you can exploit together, for example, with the correlation length to guess how the function should behave in between. So, and this is also why we opted for GPR. At the beginning, we wanted to be very, very fancy and use a neural network, okay? Because we wanted to follow the trends of modern society, but we failed. The reason is that it was not reproducing this graceful behavior outside the training domain. So the network was just extrapolating the behavior, but it was not predicting large uncertainties where you don't have enough observations. So we were very unhappy, but that's life. So at the end, our idea, just to summarize, is to start from this expression that is already operative in current analysis, and to extend in such a way that you still have a sigma, but now the mu, so the mean functional behavior that you predict, it's not a constant, but it's actually a function. It depends on other parameters. So, and then we did some toy experiments. So we assumed that you have a generic theta gr parameter that could be the mass, the spin, whatever, your favorite one, and you have a deviational parameter. So we generated mock data that you see here in gray. So mock contours, two-dimensional contours. So of course, it's a very simplified problem. We didn't solve the problem, the full problem. Okay, this was an explorative paper to explore whether the technique works in simple cases, and like, well, particularly in a two-dimensional case in which you only have a one-dimensional deviational parameter that depends on the one-dimensional GR parameters. So what we found is that, okay, let's assume you observe this. So you run the machine and you see that, so the black curve was the true functional dependence that we injected. And then there is noise. I mean, there is several reasons why you should not expect to recover your true functional function in the center of this confidence band. But the confidence band formed by all the functions extracted by the Gaussian process after our training procedure, they encompass at 95% level the true functional behavior. And also we tried a parameter estimation in which we keep this functional behavior fixed. So we already know what is the functional form. And instead of training a GPR, we do an MCMC on the coefficients of the functional form. And so we obtain the red band. This is zoomed in this region where you have most of the observations. And so what we see, it's not the same. Okay, we should not expect the same because the models are different, but it's like the level of uncertainty is consistent. So the fact that we are using a non-parametric model that doesn't know anything about the underlying functional form is not letting you lose constraining power. And then one other nice feature is that if we have a non-deterministic functional form, so we add some scatter that is not Gaussian scatter. You see, there is also a dependence on theta in this scatter that we add, so it's not trivial. So we see something in the recovery of sigma, the parameter sigma that we define here. So what you see is that sigma peaks, well, not, yes, peaks at 0 in the case of the previous slide. So basically when you don't have the scatter term, and it doesn't peak at 0 when you have the scatter term. So why is this interesting? Because sometimes when you look at a black hole or at a population of black holes and you see deviation from GR, if you see deviation from GR, the most natural explanation would be, okay, but this is not a true deviation from GR. There are, for example, environmental effects, like, I don't know, accretion disks or environments in which these BBH are happening, and you have not taken this into account. So this would be a very fair objection. Or, for example, you can have another objection, which is, okay, you probably have neglected some dependency. Like, for example, you are probing the dependence of the quasi-normal modes on the mass, but you didn't take the spin into account, or vice versa. Or or you didn't take into account, I don't know, the degree of precession of the initial spins. So there are many reasons why, for example, you wouldn't take all the variables into account. Sometimes they have a small effect, like especially precession right now, but it can be an effect that it's small, but then one day will be visible. So so this shows that this pipeline, this approach is robust to this effect. So if you have a deterministic underlying trend plus some, say, environmental scatters, you will be able to recover it. So like, at least you will be able to say there is an environmental effect on top of a deterministic one. You will not be able to separate them. So what you see here is not So this confidence region here is not the deterministic part of the deviation. So you can only reconstruct like the whole the whole delta y. So you cannot set this entangled f and epsilon q, because of course you don't know what is. Yeah, so now you know that q is theta squared, but in general you don't. So you are only sensitive to the general shape of delta y, but at least you know that there is some underlying non-deterministic process happening. Okay, and while you don't know this with the usual approach, the approach that is based on this equation, because of course here now the sigma here is a different sigma. Now this sigma is a variance, sorry, sigma squared is a variance, and this variance should account for all the possible variance in the population, not only the variance due to stochasticities, but also the variance due to the fact that you change the mass and the spin of the black hole for this event, and then you will change the value of this parameter. And all this variance enters this sigma, while our sigma, this sigma, it only accounts for stochasticities, okay? The variance due to the dependence from the other parameters is captured by the Gaussian process, so it doesn't enter the sigma. So this is a very nice, thing that we get. So this is funny. So we introduced sigma as a regularizer actually at the beginning, because when you do Monte Carlo integrals, you cannot do Monte Carlo integrals of deltas. So we wanted this to be a delta delta Dirac of delta y equal mu, but we couldn't do this inside a Monte Carlo integral. And also approximating the delta with the very big Gaussian was prone to numerical instability. So we say, okay, you know what? It's just one more parameter. Let's infer one more parameter. Let's assume it's and then we, after a brainstorm, we found that okay, we can exploit this parameter to say something about the underlying. Okay, so I made a digression on the creative process behind its. I thought it was interesting to know what was happening behind. So then this is what we get from applying this framework to current data. So basically nothing, because so these are final spins of the remnant black holes, and this is deviations in parameters, and you see they are very loosely constrained. I mean, I wouldn't even call this a constraint, it's more than 100%. But it is consistent with what I was showing you before. I mean, this is just to show that you can do this when you will have enough data. Now you don't. So when you apply this to current data, you get no deviation from GR throughout the parameter space of the spin. Okay, then, okay, this is just to show that there is an alternative way, which I already introduced at the beginning of the talk, which is, okay, why don't you just solve your beyond GR theories? Okay, why do you want to do this, non-parametric approach? Probably you should invest more into, solving all the possible theories of GR. True. I mean, this is a good argument. I think that both things are useful. First, because you will never be sure that you are, that your theorists have written down all the possible beyond GR theories, and also because it is absolutely not easy to solve the spectra for beyond GR theories, even for theories that are already formulated. But recently, like in the recent 2 or 3 years, that there has been measured developments in this field. So this is just to say that yes, so there is the complementary approach of people actually solving the spectra for beyond GR theories, and I think that they are truly complementary approach in the sense that suppose that this pipeline detects a shape here, then you will go to your theorist and you will say, look, is there a theory among your pet theory collection that reproduces this behavior? And maybe yes, maybe no, but it's important. But I mean, it's important to also solve the spectra, because I mean, it's not enough to say, okay, we see a deviation in the deviational parameter. Yeah, sure, but we want to know about the theory, not about the deviational parameter. So ultimately, these two things should go together. Then, even if, yeah, I already touched upon this. I mean, even after you discover a deviation from GR, you are not actually discovering necessarily a deviation from GR. You are probably discovering systematic effects. What is a systematic effect? So like my model is wrong. So a systematic effect is the typical situation that happens when your model is wrong. Like for example, so in GW astronomy, there is a lot of systematic effects right now because when you have a binary black hole and you want to know what is the waveform, there is no clean way of knowing the waveform. So it's a really it's a hard it's a hard feat to extract the waveform from the dynamics of the theory and the dynamics of the two orbiting objects. So this is a whole research field, and but right now, so there are clear indications that current observations are affected by systematic effects, meaning that like this program of writing down the waveforms from the phenomenological fact that two compact objects are orbiting each other is not completed. Okay, which means so from the one side, okay, this of course stimulates waveform development. From the other side, it also gives value to black hole spectroscopy, because in that case, at least you know the functional form of the signal. It is a superimposition of sinusoids. So then, of course, so you can tune the coefficients of the sinusoids, but at least you know the functional form of the signal, that you know it should be a superimposition of decaying sinusoids at special frequencies. Now, but even in the case of black hole ring downs, you might have systematic effects, and you might ask why. So the reason is that, okay, you have frequencies and damping times. They can be computed very well because thanks to Tucholsky's equation, which is a beautiful equation that describes perturbations of black hole, linear perturbations of black holes in GR. So you can compute frequencies and damping times at arbitrary precision, but you cannot compute the excitation factors of the sinusoids. These are very difficult to compute. They cannot be predicted from simple master equations. And what people do right now is to deduce them from numerical relativity simulations. Why? Because they depend on the initial conditions. So suppose that you have the same black holes so you have two black holes that are the same mass and same spin, but one formed from a head-on collision, and the other one formed from a binary coalescence. So they will have the same quasi-normal modes, so same frequencies, same damping times, because the mass is the same and the spin is the same. But which quasi-normal modes are excited and which are not, this will differ in the two cases, because it will depend on the initial conditions. So how the black hole formed. And there is no simple way of doing this calculation analytically. So what people do is the following. So you simulate as much, for example, binary black holes that you can numerically. And there are not many. So like right now, SXS, which is a catalog of binary black hole simulations, they are doing this since almost 2 decades, I would say, and they have 2K simulations. 2K simulations are not many. So if you think about it, the parameter space is 7-dimensional. So you have mass ratio. So you have three spin components for black hole 1 and 3 spins components for black hole 2. So in a 7-dimensional parameter space, having 2K simulations, I mean, it's not a big thing, because 2 to the power of 1/7, I mean, it's not, I mean, you are not even spacing each dimension in the parameter space with 10 bins, no? So So you have to play well with the data to understand what are the trends in the parameter space. So in this case, it's easy. So you have many simulations with no spin, with vanishing spins, and spanning the mass ratio. So these are the excitation amplitudes of several quasi-normal modes depending on the mass ratio. And you see by eye that there is a trend. Okay, so you say, okay, sure, I cannot do this pen and paper, or I cannot do this, from a master equation, but I can connect the dots decently. No? Sure, but why? Because this is a one-dimensional problem. Also, this is a one-dimensional problem. You fix the mass ratio, you change only the primary spin. Okay, sure. I see a tendency in the parameter space, but it's not as easy as this in the more in a more complete problem of a 7-dimensional parameter space, and not even in a 3-dimensional parameter space. So there have been efforts to capture these trends of ring-down modeling of the excitation amplitudes in the 3D case. What is the 3D case? Is the case in which the spins are aligned. So you only have mass ratio and the magnitude of the spins. So you have no precession. Okay, so this is the dynamic. So in this case, that there are fits that fit the excitation amplitudes for in closed forms, basically expanding in very, very large, polynomial expressions, adding terms, of all possible degrees of these three parameters, Q, K1, and K2. So we thought, okay, wait, yes, it's doing it. So we thought, okay, can we use Gaussian regression to do this as well? Because now it's a similar problem. So I want to reconstruct the functional behavior in which only part of the parameter space is filled with data, and I have no idea what is the functional behavior. No, so and I don't want to put tens of polynomial expressions. And the answer was positive. So like we can do this, like we can reproduce we can interpolate this numerical simulation data as well as, so this mu GPR, so this orange lines is ours, and these are the green and blue are fits that are well established in the literature. So we can do this for the 3-dimensional case. The 3-dimensional case, which you could decently do that with closed form expressions. So this was just to showcase the technique in a region in which you have a benchmark, and the benchmark is this previous fits. So we released it as a package that can be installed and used. You have one benefit, by the way, when you use GPR, that GPR does not just give you the value of the function at a particular point, it also estimates the uncertainty of your fit. Like if you don't have, like you can see here, no? So here you don't have data, you have large uncertainty. Like here, for example, you have a gap, you have a little bit tough, shallow band. So use this to be less sensitive to systematic effects. So if I not only know what is my waveform at this point, but also what is the uncertainty of my waveform at this point, it's better than nothing. No, so I can at least try to average my model when I do parameter estimation. And then these results were for the 3D case. So quasi-circular, spin-aligned binary black holes. So there is work, not with GPR, still with closed form expressions to incorporate eccentricity. And then we recently released an expansion of this work in which we look at, which was our goal from the very beginning. We look at the 7D case. So can we predict amplitudes for 7D BPH? So when also the spins are precessing, and this is interesting because, we didn't know at the time when we started the project. But recently, the LVK collaboration has released a couple of events that, because of precession, they show inconsistencies in the recovered parameters when they are estimated with different waveform models. So it would be interesting to apply this model. So to use this model to do the parameter estimation of these events and see what we recover, because at least we know in this case it's a simpler description. We should expect less systematic effects. Then finally, how much time do I have? 0. Okay. Then this is just to say, okay, then it will be 1 minute. So that you can use deep learning to do parameter estimation, and we didn't start from scratch. We are on the shoulder of giants, so there is a lot of work of using deep learning to do parameter estimation. And why do you want to do this instead of doing the regular parameter estimation? Because, for example, you want to be less prone to systematics when you do noise estimation. So when you estimate noise, you assume it is Gaussian, there is a BSD, blah, blah, blah. So this simplifying assumptions sometimes that they are not optimal. So you want to be resilient to that and for other reasons. Anyways, so we showcased that for ring down, we can do parameter estimation using deep learning, and our parameter estimation is similar to a Monte Carlo Markov chain or nested sampling parameter estimation. And we use, without going into the details, we use so-called neural density estimators, so which are neural networks that are optimized to estimate a probability density. Then, let me finish. So conclusion. So we are, transitioning from the beginning of gravitational wave astronomy towards the next decades in which gravitational wave astronomy will become a precise science, but precision comes with challenges. So challenges about noise estimation, about source modeling, about how do you model effects that are somewhat unexpected. So how do you test the theories to model possible deviations from the theories? How do you quantify your uncertainties on these deviations or on your waveforms that you are modeling? So I hope that I have shown that you can tackle these challenges with machine learning and deep learning. So I'm sure you can also tackle the challenges also with other techniques. I'm not saying that this is the only way to do, but that at least there is a possible way to do that is rooted into the progresses of machine learning and deep learning. And that's it. Thank you.
Thank you very much. Question?
Very nice talk, thank you. I have a question about the Gaussian process regressions, because you predict the posterior sample, but I want to ask if there was any way to obtain a functional form, like with symbolic regression or something, like a mathematically explainable function. Will that be useful in the in explainability? That's it.
Okay. Okay. So sub question 1, yes. So I think that you could, go for, having a functional expression that is symbolic. So, but explainability, I am not sure, for the following reason, that for sure the algorithm of symbolic regression will give you like a symbolic form that reproduces the trend, but it doesn't mean that, how do you connect this with the solution from the theory anyways, no? So it could just be one of the many symbolic expressions that reproduce the data. It doesn't mean that it matches, some function. Yeah, yes. So that's why I don't know if it would help explainability better than just plotting the result in the parameter space. And also, for example, when you solve the perturbed equations of black holes in general relativity, you do not get the functional form for the quasi-normal modes. You get tabular values anyways. So, and then you can interpolate them with, I don't know, Chebyshev, polynomial, or algebraic polynomial, whatever, power polynomials, fine. I don't think that the focus should be on what is the functional form in the sense of the algebraic form of the functional form, but just what is the trend in the parameter space. So can we plot thing in the parameter space?
So I'm wondering, it looks like right now the limiting factor is the precision of the measurements, of the gravitational wave measurements. So at what level the precision of the waveforms and the systematics in the waveforms start becoming important for your inference, for measuring the beyond GR?
It's already happening now.
But it looks like from your results, the sevens are much larger. Yeah, like here.
Yes, true. But okay, in the new release, so no event of the new release, the 04A release was put in this inferences because we were working on this paper before. But there is an event, for example, in the new release that shows signs of deviations from GR in the post-merger. So the ring down, but also a little bit earlier than the ring down, but after the peak of the energy emission. So it shows deviations. It shows also strong deviations, but so the team that analyzed this event in the LBK collaboration, they performed some simulated studies of injecting with a waveform and recovery with another waveform model, and they found the existence of systematics. So they found that the waveform models could not reproduce the same parameters when applied to what should be the same signal. So this is already happening now. So it's not well understood. So if you read that paper, they do not conclude anything. So they do not say it's a deviation from GR. They do not say it's a systematics. They say we do not understand the systematics enough to claim that this is a deviation from GR. So I think this is already happening now.
And the follow-up to that, is there any direction in which the waveforms would be improved? I mean, which is the direction that you would think the community should go in improving the waveforms in order to reduce the systematics? What are the most important factors?
So this is a very tough question, because there is an obvious thing that should be done but cannot be done, which is having thousands of numerical simulations. So this would be the best way, I would say, to do this. But cannot be done because from the high performance computing perspective, it is unfeasible to pretend this in the short term. What is being explored right now, not by me, but I know it's being explored, is insights from perturbative analytical approaches. So there is this research line that is called self-force approach to the two-body problem, that is trying to expand the waveforms in powers of Q, for example. That they know it's not good when Q is equal to 1. So it is the Emery limit. Okay, so they expand around the Emery limit. And from the other side, there is the EOB approach. That is it's called effective one body. That they take something that is not an Emery and they map into effectively parameterized Emery. So and they are trying to to meet in between. But ultimately, I think so this can improve the precision for sure. But ultimately, I think that the precision can only improve with more numerical simulation. So we can only hope that these efforts, the combined efforts, they gradually decrease the non-accuracies in the waveforms. Then, for example, there is a waveform model that is called NR-SAR, which means numerical relativity surrogate, which is based on something similar to what I shown in this slide. So they do a surrogate of the whole waveform. So it's a very ambitious project, and in some parameter space, this has much less systematics than other approaches because it can incorporate precession. Precession effects, for example, are very difficult to model analytically. So the other waveform model, they use tricks. They go to a special non-inertial frame called the co-precessing frame, blah, blah, blah. Okay. And this comes with many approximations. The surrogate is very direct. It's complicated. I know it's a complicated answer. And I cannot say. I think I cannot answer better than it's unsatisfactory. I would say a little bit this answer, but I think there is no better answer.
Okay, let's all thank Costantino again. And best of luck with your.
Thank you.